Okay, our focus here is going to be analyzing truss systems. This is an example of the truss that we are going to be analyzing. A truss is made up of individual members which are connected together by pins. It's important to note that if any member of a truss fails, the entire truss structure will collapse. So each individual member needs to be able to support its load in order for the truss to be able to stay standing. Our truss is going to have in this example, an 800-pound downward force pulling on it, and it's going to be supported at each end. At one end, it's going to be supported by what we call a pinned connection, and at the other end, it's going to be supported by what we call a roller connection. If we look a little bit closer at our pin connection and our roller connection, we can see that the pin connection, although it will pivot, the pin connection is locked in both the X and Y direction, whereas the roller connection is locked in the Y direction, but does allow for horizontal movement. And therefore, there will not be an X reaction force at that roller connection. There will only be a Y reaction force. And those reaction forces are what overcome our downward force pulling on this truss system. We're going to, for the sake of this example, we're going to again assume that that's 800 pounds. So let's go ahead and start solving for our reaction forces as well as the amount of force that ends up on each member of this truss system. The first step is going to be to draw our truss system. So we're going to go ahead and draw our members starting with a point and one member and another member. And then we have a vertical member in this direction and a diagonal down to this point. Now the dimensions of our truss are 6 inches, 6 inches, and 10 inches. And we have an 800-pound downward force acting on our truss system. Keeping that truss system in static equilibrium are our supports. So at one end, we have a pinned connection. And we draw a pinned connection like this. And at the other end, we have a roller connection. Let's go ahead and label the points of our truss system. So we're going to go ahead and call this point A, we'll call this point B, we'll call this point C, and we'll call this point D. Now one of the first things that we need to do is we need to replace our pin and our roller connection with the proper reaction forces. And we just showed the fact that a roller connection only experiences a reaction force in one direction, and that in this case is the Y direction. So I'm going to go ahead and erase my symbol for my roller connection, and I'm going to replace that with a Y reaction force, which happens to be at point A. So I'm going to go ahead and call that reaction force AY. I'm going to go ahead and replace my pin connection with 2 reaction forces. One in the Y direction, which I'm going to call reaction force CY, and one in the X direction, which I'm going to call reaction force reaction force CX. So those are my reaction forces. Now before I can go any further, one of the things that I need to do is I need to determine if this is what we call a statically determinate system. If it is statically determinate, I can use what's called the method of joints to solve for my member and my reaction forces. If this structure is not statically determinate, it means we have what are called redundant members or redundant supports in this design. Now engineers do build in redundant supports into their design for multiple different reasons. One of the most common being, if there's a failure of one member, that redundant member becomes a backup. Other times redundant members are put in place in order to make sure that to hold things in place during the assembly process, and then they're just left there. So redundant members are used in the actual construction of a truss. But what they create is too many variables to be able to actually solve for this truss system. So what we have to do is we have to create a truss system that does not have redundant members in it and redundant reactions in it in order to be able to solve. It's also kind of the most efficient design because we don't have any members that are not contributing to the support of that system. So we're going to go ahead and calculate that. And the formula that allows us to determine if a structure is statically determinate is 2 times the number of joints should be equal to the number of members plus the number of reaction forces. So in this case, we have 4 joints. 4 times 2 is 8. We have 5 members and 3 reaction forces, and therefore we have 8 here as well. This tells us that this is statically determinate. It means that we have enough formulas available to solve for the number of unknown variables that we have in this case. So at that point, we are ready to start solving this. And the first step in that process is we need to go ahead and solve for our reaction forces. But before we do that, let's talk about what it is that we are going to be calculating in this truss system. So we are going to be solving for several different things. Our 5 member forces as well as our reaction forces. So we are going to be solving for reaction force Cx. We are going to be solving for reaction force Cy. We are going to be solving for reaction force Ay. In addition to that, we are going to be solving for each of our members. So we're going to be solving for the force on member AB. FAB equals. We are going to be solving for the force on BC. FBC equals. We are going to be solving for the amount of force on member AD. So FAD equals. We're going to be solving for the amount of force on DC. FDC equals. And the amount of force on member DB. FDB equals. So this is now going to allow us to be able to have a plan as we work through this problem. And the first step is solving for our reaction forces. Now, when we go to do that, what I'd like to do is I'd like to change our thinking a little bit here. Instead of thinking this truss as being individual members, let's think of this as being one solid beam with a 500-pound force pulling downward. If we think that way, we can use our moment formulas to determine those reaction forces. So I'm going to go ahead and just kind of redraw this as a solid beam, and we're going to ignore the fact that it's a truss system just for the calculation of our reaction forces. So I'm going to draw this, as I said, like a solid beam. And remember that we have a Y reaction force at one end, which we're calling reaction force Cy. We have an X reaction force, which we're calling reaction force Cx. And then we also have a reaction force over here that we're calling reaction force Ay. And 6 feet away, we have an 800-pound downward force. So we have a dimension of 6 feet and a dimension of 10 feet. Now, we want to think of this as functioning like a lever. And our fulcrum of our lever are points A and point C. So we want to pick one point to work from. And it really doesn't matter which point we choose to work from. So for the sake of simplicity, I'm just going to start from point A. So let's picture that this is a lever. We learned about levers already. And in this case, so we have our pivot point, which is point A. That 800-pound downward force, if we think about this logically, is trying to make this lever rotate in a clockwise direction. That 800 pounds is trying to make this thing rotate clockwise about point A. We know that it's not rotating clockwise. And why isn't it rotating clockwise? It's not rotating clockwise because reaction force Cy is stopping it from rotating clockwise. Well, knowing that, we can solve for reaction force Cy. This is how we do this. We're going to go ahead and set up an equilibrium equation. And we're going to say that 800 pounds times 6 feet. 800 pounds times 6 feet. Except that 800 pounds times 6 feet is acting in a downward direction, and this would be a clockwise moment, which we actually refer to as a negative moment. So we're going to say negative 800 pounds times 6 feet, and you'll see why that's important in a second. We're going to add to that reaction force Cy times, now be careful here, it's not times 10 feet, because we're focusing everything on our pivot point, on our fulcrum, which is at point A. It is reaction force Cy times 16 feet. So reaction force Cy times 16 feet needs to add up to 0. Reaction force Cy times 16 feet equals 0. So we now have one unknown variable, reaction force Cy, that we can solve for in this equation. And the first thing that I would do is I think I would combine my terms and say 800 pounds times 6 feet. Okay, so 800 pounds times 6 feet gives me 4,800 foot-pounds. So 4,000 negative, I should say, 4,800 foot-pounds plus reaction force Cy times 16 feet equals 0. So negative 4,800 foot-pounds times reaction force Cy, or plus reaction force Cy times 16 feet equals 0. So I think my next step would be, we'll go ahead and add 4,800 pounds to each side of my equation. So we end up with reaction force Cy times 16 feet equals 4,800 foot-pounds. Now, to get reaction force Cy by itself, I'm going to divide both sides by 16 feet. The 16 feet cancel over here. Divide by 16 feet. And what I end up with is reaction force Cy when I divide 4,800 by 16. So we'll say 4,800 divided by 16. We end up with reaction force Cy equal to 300 pounds. So let's go back up and talk about what that actually means. That means reaction force Cy is equal to 300 pounds. Positive 300 pounds because it's in the upward direction, so we'll update our drawing to 300 pounds. And what that means is out of this 800-pound downward force, reaction force Cy is holding or supporting 300 pounds of that. Now, does that make logical sense? We have a total of 800 pounds being supported by two reaction forces, two vertical reaction forces, and 300 pounds is being supported by reaction force Cy. And the answer is yes, that does make sense, because reaction force Cy is a longer distance from that applied force, so it's going to share less of that load. Now, we could reverse this and go through this whole process again. We could make reaction force Cy, or point C, our pivot point, or our fulcrum, and we could go through and do the moments equation again. Or we can use what we know about statics, which is that everything adds up to 0, and we can say, let's look at what forces we have in the y direction. So I'm going to scroll down a little bit here. And we have 3 forces in the y direction. We have negative 800 pounds, we have positive 300 pounds, and we have reaction force AY. And we know that those need to add up to 0. So we can go ahead and set up an equation that says reaction force AY minus 800 pounds plus 300 pounds, which is our reaction force CY, equals 0. So the first thing I'm going to do is get rid of my negative by adding 800 pounds to both sides of the equation. Or I could also combine my terms. Maybe that would make more sense. And I can say negative 800 plus 300. So we have reaction force AY minus 500 pounds equals 0. Now I can add 500 pounds to both sides, and I have reaction force AY equals 500 pounds. So in that case, reaction force AY is 500 pounds. Let's go ahead and update our drawings. 500 pounds. Reaction force AY is 500 pounds. Reaction force AY up here, we'll draw that as 500 pounds. So we now know our Y reaction forces are equal to 300 pounds at reaction force CY and 500 pounds at reaction force AY, which adds up to the total external downward force of 500 pounds. Now, again, all we focused on at this point are our external forces. We have not started working on our internal forces yet. Now, another thing that I want to point out to you is that do we have any external forces aside from our reaction force CX that are acting in the X direction? And the answer to that is no. Our only external force that we see represented is 800 pounds downward. Therefore, our horizontal forces are equal to 0. And in this case, reaction force CX is going to be equal to 0 pounds. We're now just about ready to start solving for the individual members, but before we can do that, we need to know what angles we have at point A and point C. We could also solve at point B, but I will tell you that we don't really need to. So we're just going to worry about A and C right now, and we're going to use our trig functions in order to be able to do that. So I'll scroll down a little bit. Remember, we have at point A, we have a 6 foot and a 6 foot dimension. We have an adjacent and an opposite side that are equal to one another. In this case, 6 feet and 6 feet. I'm going to change this to feet. We're going to assume that the model is a scale. So although it is 6 inches in the actual model, we have been using feet. So to save any confusion on that, I'm going to change that to feet. We will just assume that our model is in a 1 inch to 1 foot scale. Obviously, I wasn't going to build a model that was 16 feet long and 6 feet tall. So we'll go ahead and we know, based on the fact that we have a 6 foot adjacent side and a 6 foot opposite side, that our angle in this case is going to be 45 degrees. So angle A is 45 degrees. Angle C is not quite that simple. We need to use our trig functions in order to solve for angle C. So I'll go ahead and scroll down a little bit and we will do that. So for angle C, we have a height of 6 feet and we have an adjacent side of 10 feet. Now, we are trying to find angle C. Think about our trig functions. What trig function do we have that involves the opposite side and the adjacent side? And the answer to that is tangent. So the way we would set this up is we would say that the tangent of our angle C is equal to the opposite, 6 feet, over 10 feet. And I want to show you how we would plug this into a calculator. We want to be careful with parentheses to get this right. So when we plug this into our calculator, we are going to say that 6 feet, we are going to hit the shift button. That's going to get us to our inverse tangent. We use inverse tangent when we want to find an angle. So hit the shift button, followed by our tangent button. Then we're going to open up a set of parentheses, and we are going to put in 6 divided by 10, and we'll go ahead and close out our parentheses and hit the equals button, and we end up with an angle of 30.963 degrees. 2 decimal places is plenty, so 30.96 degrees. So angle C is equal to 30.96 degrees. Let's go ahead and update our drawing at this point. So angle C is 30.96 degrees. That's going to be important in terms of solving this. The next step is we are going to create free body diagrams for each of our individual points. And we want to arrange these free body diagrams in such a way so that we are able to visualize how they connect with one another. So we are going to create a separate free body diagram for point A, point B, point C, and point D. So we'll go ahead and we'll scroll down a little bit and we'll set those up. Now it's important to note the only thing we're going to focus on are the forces acting on those individual points. We are ignoring everything else when we are focused on a specific point. So let me scroll down and we'll go ahead and start setting up these free body diagrams. So let's start at point A. So I'm going to go ahead and create the free body diagram for point A. All I'm concerned about at point A is what forces are acting specifically on point A. Well, I have member AB. I also have member AD. But in addition to that, I have my reaction force in the y direction, which is reaction force AY, which I happen to know equals 500 pounds. The next point that I'll focus on is point D. So I'll go ahead and draw a free body diagram for point D. And what do I have there? I have negative 800 pounds. I also have member DB, or BD, doesn't matter if you switch the order. I also have member AD. Notice I'm duplicating that, but that's okay because it's a separate free body diagram for point D. This is for point D. And I also have point DC. And that pretty much covers my free body diagram for point D. I'm also going to draw a free body diagram over here for point C. And what forces do I have acting on point C? Well, I have reaction force CX, which I happen to know equals 0. I have reaction force CY, which I happen to know is positive 300 pounds. I have member BC, and I also have member DC. And then lastly, I'll go ahead and I'll draw my free body diagram for point B. For point B, I have member AB, I have member DB, and I have member BC. Now, I forgot to mention something really important. We are assuming at this moment that all of our member forces are in tension. Now, let's go back to our original design. It is impossible for all of our member forces to be in tension. We know that that can't be true. However, that assumption will make things easier for us for the time being. as we find out that we are false, and I will show you how we find out that we are false, we will correct these to either compression or tension based on what we find out they actually are. Before we go any further with this, I want to take, at point A, I want to take my angular force and I want to convert it into its x and y components. That will make this much easier to work with. So what I'm going to do is I'm actually going to replace AB in this free body diagram with ABX and ABY. And remember, we have those formulas that we use for doing that. So I'm going to draw this in red before I go ahead and erase it. And I know that AB is acting in an upward and a right direction. So I'm going to have an x component and I'm going to have a y component of AB. So we'll go ahead and we'll draw this as ABY. And we'll go ahead and we'll draw this as ABX. And that allows me to now erase AB. I have replaced it with its x and y components. So I'm going to go ahead and erase it so I don't have confusion. And while I'm doing that, why don't I go ahead and do the same thing for BC. So I have BCX as well as BCY. And again, BC is acting in both the negative x direction and the positive y direction. So now that allows me to be able to eliminate BC. I'm not going to worry about doing this at point B just yet because it actually turns out I'm not going to need to. And in most cases, I don't end up needing to work to that point. If I had to go back later and find that, I could. Now, what I want to do is I want to exchange this ABY for the formula that I would use to find it. Well, how do I find ABY? ABY is really AB times the sine of my angle, which was 45 degrees. So ABY is going to be AB times the sine of 45 degrees. And ABX is going to be AB times the cosine of 45 degrees. Remember those formulas that we put in our notebook? That's where those come into play. Y sine and cosine, well, in the case of ABY, I'm dealing with the opposite side as well as the hypotenuse. The hypotenuse being the original AB force, the opposite side being ABY. In the case of ABX, I'm dealing with the hypotenuse and the adjacent side. The adjacent side being my ABX and the hypotenuse being the original AB force. So I can do the same thing over here at BC as well. So instead of BCX, I'm going to say BC times the cosine of, let me double check my angle. You probably already know it, but it was 30.96 degrees. 30.96 degrees. And BCY, I'll write over here, is BC times the sine of 30.96 degrees, and that really blends together, so I'm going to go ahead and fix that so we can see this. BC times the sine of 30.96 degrees. The smartboard is a little bit thick to work with the markers, but now I can take my free body diagrams and I'm going to pick the free body diagram that has the least number of unknown values in it. And at first glance, the one that I look at that I see having, in my opinion, the least number of unknown values is point A. So I think I'm going to start at point A, conveniently enough. And what I want to do is I want to set up equilibrium equations for point A. So I can decide if I want to start with X or Y. I think in this case, I'm going to go ahead. No, actually I can't, because I have two unknown values in the X direction. I have only one unknown in the Y direction, so I do have to start with Y. I had that wrong the first time. So let's look at just at point A. And here's the key with free body diagrams. Focus on one thing at a time. only point A and only forces in the y direction. Well, what do I have in the y direction at point A? I have RAY and I have AB times the sine of 45. That's it. Two things. And only one of them is an unknown. So I have an equation with one unknown variable. I can work with that. So I'm going to go ahead and set up this equation. And I'm going to say that RAY, so 500 pounds, plus AB times the sine of 45 equals 0, our favorite number in statics. It has to be 0 because this thing is not accelerating or decelerating. Now, I'm going to go ahead and get I want to work on getting my AB by itself, so I'm going to subtract 500 pounds from both sides, and what I end up with is AB times the sine of 45 equal to negative 500 pounds. Scroll down a little further here, and to get AB by itself, I'm going to divide both sides by the sine of 45 degrees, and what I end up with is AB equals negative 500 pounds divided by the sine of 45. And again, I want to show you how I'd like you to put that into your calculator, because the way that you do that is very important. So what I'm going to go ahead and do is I'm going to type into my calculator negative 500, and I'm going to open up a set of, I'm going to hit divided by, and then I'm going to open up a set of parentheses. I'm going to hit my sign button, and I'm going to type in 45, and then I'm going to close out my parentheses. Hit my equals button, and I end up with negative 707.10, or 11 pounds if we round. Well, wait a minute here. How can I have a negative force on a member? What does that mean? The answer is I can't. Remember I said that we assumed that everything was in tension, but we knew that it was physically impossible for it to be in tension? Well, a negative number tells me that my assumption of tension was wrong, and therefore that member is actually in compression. Now, if I didn't assume everything, I could assume everything was in compression if I wanted to. And then it would be the opposite. Or I could take a guess. And when I originally learned how to do these, that's how I was taught. I was taught to take an educated guess. The problem with that is then I have to keep track of what my guesses were versus what the actual tension or compression was. By keeping everything in tension to start, you don't have to keep track of what we assumed. We assumed everything was in tension. Therefore, if we get a negative answer, it's in compression. So in this case, we have AB equal to 707.11 pounds of compression. So 707.11 pounds compression, and let's start updating. We need to update everything. So that was member AB that we found. So we just found the force of AB. So 707.11 pounds compression. And I'm going to go up here and I'm going to label my drawing. 707.11 pounds compression. And now that I know that, I can also update my original free body diagram that I drew, and I realize that these arrowheads actually need to face the opposite way. This arrowhead needs to face this way, this arrowhead needs to face this way. So I can now use that information to solve for member AD, because I now have a value for that I can plug in for AB. I have that 707.11 pounds that I can plug in. So now I only really have one unknown variable in the x direction at point A. Again, that's all I'm focused on right now, is the x direction at point A. So let's go ahead and set up a static equilibrium equation for that. Extend our page a little bit longer. And we're going to say that Let me just make sure I'm labeling things correctly. Positive AD, so AD plus negative, scroll up a little here, negative AB times the cosine of 45 plus negative AB times the cosine of 45 degrees equals 0. Well, I have a value to plug in for AB. So what I can then say is AD minus 707.11 pounds times the cosine of 45 degrees equals 0. I'm going to go ahead and add that to both sides, so I end up with AD equals 707.11 pounds times the cosine of 45 degrees, and I have a nice easy number I can plug into my calculator, so let's go ahead and plug that in, and I'm going to say 707.11 times the cosine, so I'll hit the cosine button, 45 equals 500.00 pounds. I'm going to call that a nice easy 500 pounds in that case. So we have 500. All right, so I end up with AD equals 500 pounds. Notice that that is a positive number, therefore my assumption of tension was correct, so I don't have to update any arrows, but I am going to go up and update my original problem. So that was member FAD, and we have 500 pounds of tension. FAD is 500 pounds tension, and that should be all of our updates, and that also covers pretty much all of our member forces that are coming off of point A. So now we're ready to move on to our next free body diagram that we feel has the least number of unknown values. So let's go ahead and update our free body diagrams down here. So we do know now that AD is 500 pounds in the positive direction, and it's in tension, so it would be negative 500 pounds here, because it's acting in the negative x direction. So if we look at our free body diagram at point D, we now have enough information to solve for both the x and y direction at point D. And the nice thing is there's no angular components there, which is kind of a nice thing to work with. So let's go ahead and knock some of those off the list. So I'm going to extend my page, and I'm just going to go ahead and I'm going to redraw that point D since we're getting a little low on the page. I have negative 800 pounds, and then I have member DB. And then I also have negative 500 pounds. Why can it be negative here? This is a common question. Why can it be negative here, but not when we're talking about a member? A member is a structural component. It can either be in tension or it can be in compression. That was one of the assumptions, by the way, that we made about the members in our truss system, is that they are either in tension or compression. So in this case, I can draw this as a negative force because now we're talking about a vector. We're talking about how that member is acting on point D, not the force inside of the member. So that member is pulling against point D to the left, to the negative x direction, and that's why I can call this negative 500 pounds. Now this is going to allow us to be able to solve also for member DC. So we'll set up our equations. Sorry, that went off the screen a little bit. So negative 500 pounds plus DC equals 0. Therefore, add 500 pounds to both sides. DC equals 500 pounds. Positive answer means our assumption of tension was correct. We can also calculate DB. Negative 800 pounds plus DB B equals 0, add 800 pounds to both sides, DB equals 800 pounds. So let's go ahead and update our list as well as our free body diagrams. So member BD is equal to, or DB is equal to 800 pounds, and that is tension. And member DC is equal to 500 pounds, and again that is tension. And look what we're down to. We're down to one member left to solve for. So 800 pounds of tension, 500 pounds of tension, and the last member that we need to solve for is member BC. And we could actually approach that two different ways, and I'm going to talk about the two different ways that we could approach that. So let's go back to our free body diagram for member BC. Now, or for point C, I should say. We could use the X component or the Y component to solve for it. We really don't need to use both. The only way we would actually use both is if we really wanted to confirm that we have the correct answer. But we can use either. The one that I prefer to use, though, is the reaction force Cy. The reason being, that came out to an even number. There was no rounding involved. There was some rounding involved in calculating that 500 pounds. So theoretically, we could have some rounding error. It's very small, and you're going to get the correct answer either way. But I'm going to go ahead and work off of my reaction force rather than off of my 500 pounds, my horizontal component. But again, either way would get you to the correct answer. So let's go ahead and set up our static equilibrium equation. So we have BC times the cosine of BC times the sine. We're going to use the vertical direction. BC times the sine of 30.96. BC times the sine, not sim, of 30.96 degrees plus 300 pounds, reaction force Cy, equals 0. And we can now use this to solve. We really have one unknown variable, which is BC. First thing that we're going to do is subtract 300 pounds from both sides. That seems like the easiest thing to do. So we have BC times the sine of 30.96 degrees equals negative 300 pounds. To get BC by itself, we'll divide both sides by the sine of 30.96. It cancels on this side, and we end up with BC equal to negative 300 over the sine of 30.96. And when I plug that into my calculator, again, be very careful how you do this. I'm going to go ahead and plug in negative 300 divided by, open up a set of parentheses, sine 30.96, close my parentheses, I end up with 583.15 pounds. I'm sorry, negative 583.1 pounds. I didn't put the negative sign before the 300 there. So it's negative 583. BC equals negative 583. But wait a minute, it's a member force. It can't be negative. So what does that tell us about our assumption? It tells us our assumption was wrong, and therefore that member is in compression. So 583.16 pounds of compression. 583.16 pounds of compression. 583.16 pounds of compression. That is the last unknown that we need to find. 583.16 pounds of compression. And we have now solved for the reaction forces and the member forces throughout this entire system. So this tells us, again, remember we're using this as a scale model, but if we had this in 1 inch to 1 foot scale and we were applying 800 pounds downward, what we would end up with, and by the way, should point out to you that the forces would actually distribute the same if this was in inches rather than in feet. It's just a matter, it would be proportionate. So what that means is we have our 800 pound downward force, we have 500 pounds of tension, we have 500 pounds of tension. We would have a compression force on this member of 707.11 pounds. We would have a compression force on this member of 583.16 pounds, and we would have 800 pounds on this member. Why is that important? It's important because the structural engineers would then be able to look at this and determine whether or not each of these members were strong enough to support the load. So these calculations are important in predicting the performance of structural components. I know there's a lot of steps involved, but none of the steps are particularly difficult. If you take your time and work through these step by step, they're not too bad to solve. Have a great day, everybody. Thanks for watching.